Hi there. My name is Sarah. I'm an EMS program faculty here at UCLA Center for Pre-Hospital Care. I'm an EMT and I have my bachelor's in science and health sciences in physiology. And today I'm going to discuss with you the fundamentals of human physiology and homeostasis. Now we are going to break this down into three major parts. This first part, we're going to talk about basic homeostasis and we'll discuss pH. Here are the objectives for our lecture here today. We are going to define and explain the concepts of homeostasis and its importance to normal human functioning. We'll define metabolism, catabolism, anabolism, and how they relate to the human body. Talk about the basic steps in glycolysis and indicate the major products of ATP production. We'll define pH and its significance to the human body, and therefore understand acids, bases, acidosis, and alkalosis. Explain the difference between acidosis and alkalosis on the pH scale, and describe the purpose of the bicarbonate buffer system and how it's used in the body. And then finally close out by discussing the relationship between homeostasis and disease. To really be able to jump into this, we must start with the basics. And what is homeostasis? Well, homeostasis is a balance. It's a state of balance amongst all body systems that's needed for the body to survive and function correctly. It's a very, very careful balance the body keeps to make sure everything in it works. This is all the goal of life, is to keep us at homeostasis and keep us alive. The way we do that is through a very careful negative feedback. So if our goal here is to maintain this homeostasis, then something eventually will push us off of homeostasis. Some sort of stimulus will come and change the conditions of the body. That will be picked up by a receptor in the body, and that receptor will send that information over to a control center. Oftentimes, this is the brain. That control center will send instructions to some sort of effector in the body to cause a change. That desired effect will take place, and that will help us balance back to that very essential homeostasis. So for example, let's say we're out in the snow and we get very cold. That's our stimulus. Well, our nerves are going to pick up on that. Our receptors are going to feel that coldness, and it's going to send that information over to the brain. And the brain is going to say, hey, we need to warm up muscles. Let's start to shiver. The shivering of these muscles will bring up our body temperature and bring us back to homeostasis. And the body's doing this constantly with a ton of different systems throughout its body. And in order to maintain homeostasis, your body needs energy. It needs energy to shiver these muscles or to help you take up glucose. All different kinds of things that the body does, they all require energy. And so how do we create that energy? Well, we do that through metabolism. Metabolism refers to the chemical processes that happen within all the cells in your body that allow you to live and function. Okay, it's how we turn the food we eat into chemicals and turn those chemicals into energy. In the body, this is going to be in the form of molecules called ATP. Those are our energy molecules in the body. Now, what does that process look like? Well, metabolism is always going to start with the first process of glycolysis. Glycolysis is the process where we can take the most simple sugars that our digestive system breaks our food down into glucose and turns it into pyruvic acid. The process of turning glucose into pyruvic acid will actually create two ATP molecules. So at the very first step, we're already creating energy. Now, in aerobic metabolism, oxygen is present. So in the presence of oxygen, that pyruvic acid will enter our Krebs cycle. that will create carbon dioxide and push us into the electron transport system. Now, this electron transport system requires the input of oxygen to create 36 more ATP molecules and the byproduct of H2O, or water. And this is a really effective way of making energy, right? We ended up with 36 plus 2, 38 ATP molecules through aerobic metabolism. Now, what if for some reason oxygen is not present? Well, then instead of going through aerobic metabolism, we go through anaerobic metabolism. In the absence of oxygen, we cannot go through this whole cycle. And unfortunately, glycolysis is the extent of the energy that we can make. We can really only make those 2 ATP we make in glycolysis. So when oxygen is not present, pyruvic acid will end up breaking down into lactic acid and ethanol. Both not great things to be building up in the body. The body has a very hard time getting rid of these, and these can cause some pretty negative effects in the body, damaging tissues. So that's why it's so important that we have oxygen, so we can go through this beautiful aerobic metabolism and make all of that energy. But how does this make energy? How does the breaking down of glucose actually make energy, make these ATP molecules? It's through a process called catabolism. That's what we see right up here, catabolism. This is where we take molecules and we break them down into smaller units. The process of breaking all of these bonds, making up these molecules, will create energy. It will release energy. So we take molecules, we break it down into smaller units and energy. And this is what we're seeing in metabolism. And this allows us to take that energy to other places and go through the process of anabolism. This is where we take small units and we take energy and we can create molecules. This is how we can utilize the energy to do specific jobs within the body. Now, metabolism is just one function of many that ensure balance or homeostasis in the body. Our body has to balance many aspects to ensure that everything can function properly. In this homeostasis series, we'll discuss many different things the body balances, like water and energy, as well as our very next topic, the pH. So first, to understand the pH of the body, we have to just understand pH in general. And this is the pH scale. pH scale goes from 0 to 14. Now, 0 is the most acidic something can be. 14 is the most basic something can be, or as we call it, alkaline. And right in the middle, that's neutral. Okay, something that's super acidic is going to have lots of what we call hydrogen ions. These hydrogen ions like to make bonds and do all kinds of things, making it very reactive. Something that's really basic is lacking hydrogen ions. Again, because it really wants to make things, it makes it very reactive. That makes our most neutral something that has a good balance of hydrogen ions. In this case, we see 2 hydrogen ions to 1 oxygen, or H2O, water. And water is going to sit right here at neutral. So if water is neutral at 7, let's talk about some of the other things that we can think of and where they fall on pH scale. Stomach acid is all the way down here near 0. Then we think about something like coffee. Black coffee sits around a 5 on the pH scale. Then we move into the alkaline section. Normal hand soap sits around a 9 on our pH scale. And finally, bleach sits up here at a 13, and the most alkaline on the pH scale. A lot of people think that bleach is acidic, and it's actually not. It's all the way on the other side of our pH scale in the alkaline. And just like everything else in the body, our body must balance pH. It's an important part of homeostasis to be able to balance pH. How does our body do that? It does it through a system of buffer systems. One of the most important buffer systems is the bicarbonate buffer system. This is the process in which our body balances the pH of our blood. And it's done through these chemical reactions that you see here. Carbon dioxide, water, these can combine to create carbonic acid. Now, carbonic acid is a very weak acid. What do I mean by weak acid? Well, let's go back to this pH scale. A weak acid is an acid that sits very close to neutral. That means it's really close to water on the pH scale. And it means we bounce very easily back and forth between these different phases. This carbonic acid can also dissociate in a different way to hydrogen ion and bicarbonate. That hydrogen ion is what makes things acidic, right? This hydrogen ion is the status of acid, right? So if we increase hydrogen ions, we'll increase acidity. Now, we can actually change or adjust where we sit on this kind of balance by increasing or decreasing different factors. If we increase carbon dioxide, it will push us across through carbonic acid over here, and we will increase hydrogen ions. If we decrease carbon dioxide, it will pull us away, and it will decrease hydrogen ions. Now, lucky for us, we have the lungs, and the lungs can control carbon dioxide, right? Increase carbon dioxide by slowing down the breathing. We increase our hydrogen ions, and therefore we make the blood more acidic. If we decrease our carbon dioxide by breathing more, we decrease our hydrogen ions and we'll make something more alkaline, or make our blood more alkaline. Another way we can kind of adjust this buffer system is through the kidneys, because the kidneys control bicarbonate reabsorption. And that can also help us balance pH in that way. Now, when the blood becomes too acidic or has too high of hydrogen ion concentration, the bicarbonate ions, so that's these guys over here, these bicarbonate ions, they will react with this hydrogen to create carbonic acid, which can then push over here to create carbon dioxide, which will then be easily eliminated through breathing. Conversely, when the blood becomes too basic or too alkaline, there's not enough hydrogen ions, carbonic acid can dissolve into hydrogen ions and our bicarbonate to increase hydrogen ion levels and make it more acidic. It's a very delicate buffer system that relies on the lungs and the kidneys to do their job. So if we have issues with lungs or kidneys, we can affect the pH of the blood. If we affect the pH of the blood, we'll see changes in the way the lungs and kidneys work. What happens when this bicarbonate buffer system gets disturbed or gets overwhelmed? Well, that's when the blood becomes too acidic or too basic. When the blood becomes too acidic, it's called acidosis. When the blood becomes too acidic, it's called alkalosis. Now, normal blood pH sits in a very tight range between 7.35 and 7.45. Anything below a 7.35 would be considered acidosis. Now, as we spoke about, that can be because of carbon dioxide buildup. We can see it in diabetic ketoacidosis or DKA, hyperchloremic acidosis, kidney disease, lactic acidosis, poisoning with things like aspirin or ethylene glycol or methanol, and severe dehydration. On the other hand, alkalosis is when our blood pH is above 7.5. This can be due to excessive intake of bicarbonate, things like baking soda, loss of hydrochloric acid through vomiting or diarrhea or even gastric suction, the use of diuretics like water pills, kidney disease, hypokalemia or low potassium levels, and hyperventilation. All different ways that the blood can become too alkaline and will get alkalosis. And so that brings us to this last conversation of how does homeostasis relate to disease? Well, disease at its core is just disruption of homeostasis. It's the failure of a system to adapt back to homeostasis or the inability to recover. That's it for part 1 of our fundamentals of human physiology and homeostasis. Next time, we are going to take a look at homeostasis and how it interacts with oxygen and ATP a little bit more closely.